Okay, sure. So,
Yes, sir. I started the recording.
all right. Thanks, SB. So, welcome everyone to this talk. Sorry about the small delay. So, our today's speaker at Alum at Alma is Akshay Gadre. He's an assistant professor at EC department at University of Washington. He recently received his PhD at CMU, where his research operated at the intersection of wireless, mobile, and cyber physical systems, with special focus on empowering the low power IoT devices deployed on Earth and space, about which he is going to talk today. He has published at premier cyber physical systems and mobile systems venues like NSDI, Mobicom, and ICC. His work has received Best Paper Awards at IPSN 2018 and 20. He was awarded the Best Presentation Award at IPSN PhD Forum 2020. He was also awarded the ACM SIGBET 6 of Frank Anger Memorial Award 2021 for his cross-disciplinary research across embedded systems and software engineering. His work on IoT security and privacy was recognized with the Scilab Presidential Fellowship 2020-21. At University of Washington, his lab explores the upcoming application domains such as satellite IoT, agriculture, and underwater devices to apply wireless expertise for improving communication and sensing capability of these devices while preserving the security and privacy of sensor data. He's going to talk to us something about the low power IoT on Earth and space. And I feel very happy to have Akshay talking to us today. He was our student in program analysis, as well as he troubled me a lot in, I think, paradigms of programming or compiler design, one of them. And this is my opportunity to ask him a lot of questions. So, and I hope that all the other students will also join me in asking him a lot of questions. Over to you, Akshay.
Thanks, Rupesh, for the kind introduction. And hi, everyone. It feels good to be home virtually, and hopefully, I'll be there soon, maybe in December. So, hi, I'm Akshay Gadre. I'm assistant professor at UWEC, and today I'm going to talk about how we can rethink low power Internet of Things to deploy them at scale on Earth and space. But before I talk about my research, let me tell you a little bit about myself because it's an Alum at Alma talk. Uh, I basically started my undergrad at IIT Madras, where I did a dual degree with BTech honors and MTech. And during my undergrad, I explored a variety of areas. I started with complexity theory, as Jailal Sharma and some of the others might remember. And then I did a lot of courses on compilers and program analysis with Rupesh and Krishna Nandivada. And then finally, I did my master's thesis in computer networks under the guidance of Krishna Shivlingam. And you would think like, okay, this guy seems like he has everything figured out. But I did my internships in totally unrelated areas. I did an internship in human computer interaction, natural language processing, and then a combination of compilers and networks. So it's fine even if you have not figured out what you want to do, you can always keep exploring and try out new things. When I started my Carnegie Mellon journey and graduated from there, I had explored a lot more exciting areas in wireless systems, such as city scale IoT systems, high throughput wireless communication, and satellite IoT. We'll talk about a few of those today. And of course, with a lot of hard work and stuff that Rupesh already explained, I am now assistant professor at University of Washington. So I'm just a kid like many of you are at IIT Madras, and I'm happy to work with you and hope that all of you do great things. And to basically understand what do, I build wireless mobile and cyber physical systems. For instance, you would see me deploying a large-scale sensor network deployment in a city, or me carrying 5 antennas and walking around the city trying to collect data about cellular, Wi-Fi, and other types of coverage. You might see me actually flying some drones indoors to try to make them safe to operate around humans, where we can track their trajectories more accurately, etc. We also built some of the fastest wireless links at that time known to humans, where we transmitted several Gbps data using a single full duplex millimeter wave link. I also collaborated with Microsoft on building a supply chain sensing solution where you can find the integrity of product like a porcelain cup or a glass that you're gifting to a friend, and ensure that the package reaches the destination in a right manner. And of course, more recently, I've also explored communicating with satellites, where we launched 3 satellites along with our collaborators and tried communicating with them and improving communication protocols to do better communication with these satellites being deployed. And with that, let me talk about what the topic of today is. So when we talk about Internet of Things, we should think about things that are connected to Internet. Basically things like your computer, your laptops, or your mobile phones. Now, apart from these things, there's a lot of things that connect wirelessly to these devices. For example, your headphone, a printer, or a projector in a classroom that you might be listening to this lecture to. And finally, you have all seen these smart bulbs, smart switches that you can operate using a mobile phone to turn off on a fan or off a fan, or security cameras in the front of your house. These Internet of Things devices are all deployed in indoors, either in homes or offices to serve various purposes. But all they do is gather data about indoor information and then supply it to you, and then do certain actions like, okay, print a paper or project information. Now, as we started thinking about deploying these devices outdoors, let's say for an example in an urban downtown environment, we started thinking of new applications that can be developed for these kind of devices. For instance, you could have road sensors that sense whether the roads are being uh, uh, are in a good condition, and if there are potholes, those road sensors can detect us for them, and we can send maintenance staff to go and repair them. Many of the smart billing meters in India, in US, and in various other countries already communicate wirelessly, giving you accurate data every minute by minute or every hour by hour. Further, you might have also seen smart trash cans on the IIT Madras campus or in many other locations in various places, where once they are full, they just send a message to the garbage pickup company and they just come and clean the garbage. Of course, there are other utility sensors like air quality sensors that we have deployment at IIT Madras already, and we of course have flood sensors in Chennai as well. Further, apart from urban scenarios, there are various scenarios in agricultural and forest domains where you deploy some sensors for forest management or for smart farming, for example, irrigation. Now, what do you lose when you take these IoT sensors and take them outside? Well, there are two things that are ubiquitously available indoors which are not available outside. That is wireless connectivity and power supply. Hence, we need to think of a new technology that can connect these devices outdoors. And basically, that technology needs to achieve 3 things. First, it needs to be long range so that hey, you can deploy one base station and then connect a large number of devices across a large area. Second, it needs to be low power so that hey, you can power these sensors using a simple AA battery. And third, these deployments should be easy to scale, where you can just deploy a device and press a button and you can start receiving data. So they should be able to receive data from a large number of IoT devices instead of just one receiver and one transmitter. And it was with this vision that wireless experts came up with the idea of low power wide area networks technologies. These technologies are wireless technologies that connect long range IoT devices. Basically, think of it as a version of Wi-Fi that can allow you to communicate at a range of 10 kilometers and can operate for 10 years on a single AA battery. These technologies achieve these good things by reducing the data rate of the communication, and hence can achieve only a few kbps of downlink capacity from the sensor to the base station. And these are not some niche devices that I'm just using for my research and hence are useful there. In fact, 1 in every 4 industrial IoT connections which use wireless technologies will be using one of these sensors. Further, the number of such LPWAN devices is going to scale up exponentially, reaching several billions. Now, obviously, these LPWAN technologies are great, but what happens once you deploy these sensors and connect all of them? After you deploy these devices, you want to use their data to perform some inference tasks. For example, hey, what is the weather in Chennai? Or what is the weather in Seattle? Or, hey, should I irrigate my farm already? Is the soil already dry enough for me to irrigate it? Or it can help asthmatic patients to avoid pollution heavy areas in a city. A typical inference pipeline for IoT devices looks like as follows. You will have several of these devices deployed spatially, and you would use some wireless communication technology like LPWANs to collect these data. And then you will do some machine learning or statistical inference to use this data to make certain decisions, like, hey, avoid certain areas if you are breathing impaired. Well, this works perfectly, right? Well, uh, for example, let's say you are on a farm scenario, you have multiple soil moisture sensors, and if the soil moisture goes below a certain threshold, you should say, oh, you should start irrigating the soil. Now, there are two assumptions that this inference pipeline makes. First, wireless communication can enable retrieval of that data, and second, you get enough data to make useful inference. Now, unfortunately, this inference pipelines breaks down for LPWANs. The LPWANs, if you remember well, they can only transmit a small amount of data. And hence, the amount of data that can be retrieved from these large number of devices is only sparse data, that like a few of the sensors, a little few KBs of data. And because there is such a small amount of data, all the machine learning and statistical inference algorithm leads to bad inference because the amount of raw data available itself is very little. And of course, people have attempted to solve these problems in different ways, including myself, with technologies such as coherent combining, where you try to combine the data of each of these sensors, smarter MAC layers, and automated configuration. And also on the inference side, people have built technologies to do better recovery of information from the data, like sparse recovery, sketching, deep learning, and reinforcement learning, where you cooperate with the sensors. My approach instead, across my doctoral studies, has been to co-design the wireless communication and inference algorithms. And using this unified approach, I have built two solutions that I will be talking about today. Oh, by the way, I have done a lot of projects in wireless long-range connectivity, but we'll be talking about only two of the projects today. First, Project Quail enables low latency inference at scale, where you have thousands of sensors and you want a quick aggregate information. And the second project that I'll be talking about today will show you how you can get low latency imaging from satellites in space. So let's dive deep into the first project. So let's look at an example to understand what problem are we going to solve. Let's say you have a forest deployment, and in this graphic, each tree represents a large area of forest, and because these LPWAN technologies can enable a long range, you can connect thousands of such clients per base station. So a single base station and 1,000 of these sensors deployed in a forest. Let's say one day something unique happens, like a forest fire. Now, instead of retrieving data from each individual sensor, we really care about scenarios that we really care about aggregate questions that we want to answer. For example, hey, where did the fire originate? Where is it spreading? And which areas should be evacuated? These kind of unexpected events require quick information aggregation from a large number of clients. For example, we don't really care about the information from one area of the forest. We instead care about, hey, where is the fire originating and where is it spreading? And there is a stark dichotomy between the kind of deployments LPWANs were made for and the kind of responses these special queries require. The LPWANs, as I previously explained, were built, these technologies were built for occasional individual information, a short burst of information from these IoT devices. Whereas such unexpected events require special queries, which require quick information from a large number of IoT devices in the form of aggregates. Now, how will we receive data from these devices today? Well, there are few approaches that we can take to receive data from these devices. The first is, hey, let's ask every device to send information one by one. Let's say device 1 send information, device 2 send information, and you go one by one. Unfortunately, if there are thousands of such devices, it will take too much time. It's too latency intensive and may require even 3.5 hours to query 10,000 clients. The other approach could be, hey, let's sample a few of these clients and try to interpolate the data in between them. Let's query a few of these clients and then do some cool interpolation techniques get information. Unfortunately, the forest fire is in one corner of the forest. So if you don't pick that point in your sample, most of the data will be highly irrelevant. And hence, to achieve any relevant accuracy for the application, it requires high latency. There's also approaches which do like parallel decoding of collided packets, which achieves low latency and high accuracy, but does not scale to more than 4 to 6 clients. Hence, we are in a situation of trouble where a forest fire is happening and we want quick information from all of these sensors. Just to put it in contrast with prior work, LoRa can use these technologies to get data very, very slowly, whereas inference algorithms requires us to collect data from all of these clients. And in the middle lies the problem of forest fire detection. And unfortunately, using today's approach, it could take up to several hours. So can we build a magical solution to do this detection of forest fire within a few seconds instead? So basically the question boils down to, can we quickly retrieve estimate of aggregate information across LPWAN radios in a forest or in a city? And we say yes, we present quick aggregate queries on LPWANs. Before I tell you how it works, let me tell you what it does. It's a system that can perform aggregate queries on thousands of nodes within the duration of a single packet. Second, it's compatible with the two of the most popular LPWAN technologies and can do statistical, spatial, and inference queries. And finally, it does much better compared to sparse sampling solutions. So, and it really revolves around my unique approach to co-design the wireless physical layer and the inference algorithms. Let's say the goal is to get information from all of these clients. So I asked a really insane, and some even called it a ridiculous question: what is the fastest way we can send information from all of these clients to the base station? Well, here's a stupid solution: make all of them transmit at the same time. Well, all of the people who are experts in wireless in the audience would know that, hey, if all of the packets are being transmitted at the same time, all the packets would collide and you would get no information at all. But is the collided packets information truly random? Well, I noticed a pattern that was not necessarily purely random, and that was how the wireless powers of these collided packets add up. To show you a demonstrative example, let's say we have two clients. Let's say one client is transmitting some amount of energy and another client is transmitting the same amount of energy. And let's say they're transmitting simple sine waves. Okay. If the sine waves reach the destination perfectly in synchronization, where their phases are perfectly matched, you will receive twice the amplitude or 4x the power at the receiver. Now, obviously, the best case scenario is a unique scenario. There is always a worst case scenario. What if they're perfectly out of phase, in which both the signals will cancel each other out and you'll receive no signal at all at the receiver? However, if you integrate across various phases, the average case scenario is that you will receive twice the power of the individual transmission. And I really wanted to evaluate this phenomenon at a large scale. So I actually deployed 10 sensors and evaluated their collisions. And we saw this pattern of powers adding up linearly does scale to 10 clients. Now, of course, we could not deploy like 10,000 clients simultaneously because each sensor is $300. It would just require an insane amount of money. So instead, we collected a lot of data from over 150,000 GPS tagged locations, and we did trace-driven emulation of their collisions. And what we found was even more interesting. As the number of clients become larger and larger, the addition becomes closer and closer to the linear sum of powers. And you might ask, hey, why does this happen, Akshay? Well, the reason this happens is because of law of large numbers. All the other smaller errors cancel each other out, and the law of large numbers aggregates to the mean. And now that we have an approach to get a sum of some numbers, let's use it to transmit some useful information. Let's say these two sensors were measuring temperature, and one is measuring 20 degrees Celsius and another is measuring 30 degrees Celsius. We can ensure that the transmitted powers are proportional to the sensed information. For in this case, let's say they are 20 milliwatts and 30 milliwatts. I know that wireless channels are also affected by the environment, and we have a detailed solution on how to compensate for those wireless channels. But let's say we receive this 20 and 30 milliwatt. At the average case scenario, we would receive 50 milliwatt, which can be used to infer the mean temperature, right? Similarly, we can also send some simple functions of the sensed information. For example, we can send the transmit power proportional to the square of the temperature being measured. Let's say 4 milliwatt and 9 milliwatt, and at the receiver, you can use that to calculate the variance. Similarly, you can pre-multiply it with a constant and then send that information in that way, and we can receive the mean directly. And this is a kind of a very simple example. But what I really want to demonstrate here is the fact that, hey, what can this linear combination of powers achieve? Well, really, it can achieve weighted linear combinations of simple functions of the sensed information. At this point, you would say, oh, wow, this is very fantastic. So what can these weighted linear combinations really achieve? And that's what the next part will talk about. So now that we have a layer that can get us weighted linear combination of simple functions of sensed information, let's try to understand what can it really help us in inferring. So what can you do with these simple linear combinations? Well, first you can get statistical queries like I showed, like mean, median, mode, variance, the sum of the sensed data or the count of the data. Second, we can do inference queries. As many of you might be experts at neural networks, the first layer of a neural network is simply the weighted linear combination of the sensed information, which can be directly retrieved over the air instead of requesting individual information first. And this is not just for neural networks. A lot of other supervised learning methods actually have the weighted linear combinations as the first layer of their network. And finally, we can also perform spatial queries. And spatial queries are really unique, so let me show you how it works. Let's say we have a lot of sensors deployed in a forest, and there is a forest fire burning, which is basically affecting the sensed information. Think of getting information from these sensors as if retrieving a pixel of a large image from sky. And for images, we know how to compress the data very well. For example, you can do JPEG compression, which uses something like discrete cosine transform or discrete wavelet transform. And a key component of these compression algorithms is something like DCT or DWT. Most of these transforms, such as DCT or DWT, are inherently linear so that they can be performed in a quick way for fast compression. Now that we have a linear compression algorithm, we can also do this linear compression using our Quail's approach of weighted linear combinations to communicate client's contribution to the above image that we are taking from the sky of a spatial domain. This is a little bit abstract, so let me show it to you with a live example. Let's say you have a forest burning and you have a sense distribution at some sense locations. Each of these sensors will transmit their data corresponding to the contributions to various DCT components. And obviously we'll pick the top n components because they usually contain the most information. At the receiver, you will receive only a few of those components in the top left corner as it's shown in this figure. And as we know in DCT, most of the energy is concentrated at the top left part of the image, which can be used to get a rough estimate of the distribution by reconstructing it from those components. So this is a way how we can get spatial distributions from a large number of clients quickly using Quail. And thus we can apply it to the forest fire scenario. Now, is this just for forest fire? Is it useless for other applications? Definitely not. You can do a lot of other applications such as firmware polling. If you have deployed 100 sensors, you can ask, hey, how many of these sensors were upgraded to the next firmware? Or in agriculture scenario, you would want to find out, hey, should I irrigate my farm now? Or in a city, you can identify the pollution distribution. There are various other challenges that comes with wireless deployments that I will not go over because of the time limit of this talk, but I invite you to read the paper and reach out to me if you have any questions. I implemented it using actual receivers and client devices on a large campus scale test bed. We had a single base station because that's how Quail works, and we collected over 150,000 GPS tag channel measurements on a campus. As you can see, it's a large scale area with mountains, buildings, and everything. And we really wanted to evaluate on the forest fire case study because that is something that motivated our problem. So imagine there is a forest fire burning and you want to get a rough estimate of how the fire is spread. Now, of course, I did not burn a forest near my campus. It is all trace driven simulation. And we really are comparing our Quail's approach with sparse sampling approach with interpolation, as I explained previously, and an ideal Quail where all these wireless things do not affect the behavior of Quail. The first result shows that, hey, to retrieve 90% of the information, even the sparse sampling solutions do very well. And you will be saying like, hey, wait, Akshay, this means that, hey, sparse sampling works well. But remember, if you just say that the forest is green, you will be 90% correct because the forest is green all the time. It's really about the last 10% of information where these unique events are happening, which you want to retrieve. And to retrieve those final 5 or 7.5% of information, sparse sampling requires significantly more number of queries compared to a Quail solution. Note how Quail is slightly suboptimal compared to an ideal Quail, but that's how the real world is. And with that, I would like to end the discussion of the first solution, and I'll wait briefly for any questions, otherwise move on to the next project.
Yeah, one question I have is what happens to nonlinear or periodic functions which the sensors might be capable of computing?
Oh yeah, so as long as they are being computed at the sensors, that's fine. But if you want to compute non-linear sums over the air, sadly that technology is quite tough to achieve. And it's frankly almost, I would say, impossible because there is no non-linear phenomenon that we know today that we can exploit. But there are a few phenomena that people are exploring, like some kind of quantum combination of data from a large number of distributed sensors for volcano sensing. But it's not quite there yet. But
Sure,
maybe in the future it will be. Yeah.
sure. Thank you.
So let me move on to the next project and I'll take all the questions at the end. So now that we have shown a way to get low latency IoT inference at scale on terrestrial deployments, let me explain you how we can do low latency imaging from satellites. And before I explain how do we do low latency imaging from satellites, what are the satellites that we are talking about? Specifically, I'm talking about small CubeSats, which are almost like sensors in space. So CubeSats are 10 by 10 by 10 centimeter cube sensors that we just throw in space and they orbit around in Earth. And the reason they are so small is because they are cheaper to deploy. Another reason they are so easy to deploy is because they are being deployed in low Earth orbit instead of geostationary orbit. And we actually had a collaborator who was sending 3 of the satellites, which are shown in the figure, to space to investigate ranging and localization applications that they wanted to perform. And the cool thing was they were using an LPWAN technology. So I was like, hey, why not do some research on satellites? And these kind of satellites are not just being deployed around Earth. In fact, the Mars rover, which US had sent with JPL Caltech, had actually sent 2 CubeSats to even Mars to do imaging of Mars surface and get some information there. So these are not just some niche applications, these are going to be the future of space autonomy. And really, when you're thinking about low power IoT in space, you're talking about these satellites that are going around in orbit once every 8 hours, and we want to collect data from these satellites. And really, when you have these satellites traveling in space using these low power IoT technologies, there are several challenges that show up. First, obviously, is that, hey, they are much, much farther away. Instead of 10 kilometers, they are 500 kilometers away. Unfortunately for us, that's not a problem because the satellites are allowed to transmit at significantly higher power levels, and also they have very, very high antenna gain to focus on the ground. Next, there could be multiple satellites, so you would want to communicate with all of them simultaneously. And really, today's ground infrastructure is not there yet to receive from a large number of satellites in space. In fact, this is the CubeSat that we launched, which our collaborators launched in collaboration with NASA on a SpaceX rideshare mission. As you can see, at any location, the satellite is available for a very, very small time. And after that, they basically go away, and then we have to wait 8 hours to receive signals from it again. So if you're looking at a place like Chennai or in Pittsburgh or in Seattle, you'll get roughly 15 minutes of coverage every 8 hours. And one approach could be to, hey, let's try to leverage the existing satellite ground stations. And if you try to use existing satellite ground station, you will see that the latency of receiving information from satellites can be as large as 1 hour, because in various locations around the world, there is no coverage from these large base stations, because either there are no scientific deployments of ground stations, or they are too expensive to deploy in those locations because there's no useful information. Now, so the question we really wanted to ask was, hey, can we leverage all this LPWAN infrastructure that already exists in all the smart cities around the world to receive information from these satellites? And really, the idea is to leverage LoRa technology, which I've talked about in the previous project as well, at 915 megahertz. And to see the win, we can achieve significantly lower latency around the world compared to all the satellite ground stations that all the public providers provide. Okay, this is cool. So if I can somehow magically receive signals from the existing LoRa base stations, we would have reduced the latency of receiving information. Now, is it so easy to just take a terrestrial technology and send it in space and start communicating? Well, of course not. There's a lot of challenges that we need to solve to enable this low latency connectivity to CubeSats. Before I talk about the challenges, let me go over a few benefits of using LPWAN technologies for CubeSats. The first is there's a large infrastructure deployment around the world in most developed countries, including India, Europe, or even US. Next, it's already resilient to terrestrial interference because it's deployed on ground already. So it knows the ground interference and is resilient to it. And finally, it's extremely spectrum efficient. So you can deploy large number of these satellites in the sky and still receive data from all of them concurrently. So what's the catch? Well, you know how these IoT devices are deployed on ground or on vehicles, and the fastest vehicle, let's say, will be traveling around 60 meters per second, right, on Earth. Well, these satellites are traveling at the speed of 7,000 meters per second in sky. Now, because of this, the amount of Doppler, the signal that it's transmitting faces, is significantly larger. The second problem is, hey, you have HD cameras on ground, which are capturing a lot of good images. But to send them to the ground, you need a large amount of data throughput that you get usually through 5G or Wi-Fi. Unfortunately, the problem with LPWANs is it can only send a small amount of data, just a 256 byte sized packet. And basically, if you just stupidly compress the information using bit compression, you will get information which is quite useless, as you can see in this image. So because of this low bandwidth, we need to somehow do smarter compression. And thus, we need to make LoRa really understand the behavior of these space applications. To understand the problem of Doppler, let's look at the problem it causes at the receiver. Now, the Doppler that we see from satellites goes from 20 kilohertz to minus 20 kilohertz. But the packet detection limits of terrestrial receivers cannot receive those signals at such high Doppler. These are the packet detection limits of certain bandwidths of the receivers. And hence, half the packets just go unreceived. For example, if you just transmit packets from the sky naively and try to receive them, out of the 15 packets that it transmits, you will receive only 2 of them, and those also very erroneously. The second problem is you cannot send the original image because you don't have enough data to send downstream. You don't have enough bandwidth to send data downstream. So you only can send either 1-bit data, 2-bit data, or 4-bit data. And you can only send like a blurry image of the image being captured from the satellite. And hence, it's not really useful. And there have been prior LoRa CubeSats which have been deployed. However, they solve this problem using a very different approach. They are operate at lower frequency where the Doppler is much smaller, like this light blue curve that you see here. So the Doppler is not a problem. And second, they use specialized base stations, which removes the benefit of latency that we are trying to provide using LoRa, right? So because they use specialized receivers. So all these prior LoRa deployments are not really a good baseline for our system. So can we perform low latency inference on LoRa-enabled CubeSat images by leveraging this existing ground infrastructure? And of course, we say yes. We present Vista, low latency imaging and inference from LoRa-enabled CubeSats. It overcomes this throughput and Doppler constraints. It designs channel-aware data task-driven encodings to retrieve the images and achieves significant improvement in image retrieval and classification tasks over the images. To understand how, it goes back to the old approach of co-designing the wireless physical layer and inference algorithms. Again, we face a data bottleneck from the sensors to the ground, and because we don't get enough data, we can't do useful inference. In this case, we develop a Doppler resilient encoding, which does the encoding resilient to the effects of Doppler on the data bits so that it's more robust to the wireless channel over the air. And second, we build an inference decoder that can perform inference on the small amount of data being sent by the transmitter. Our approach relies on a key observation. While these are some of the first satellites being sent that use this low power wide area network technology, these are definitely not the first imaging satellites that we are sending to the sky. For example, there's a lot of data available from other imaging satellites that can be used to train these systems, such as Sentinel-2, Landsat, NOAA, or some of the Indian satellites as well. Second, the tasks performed on this data can be known a priori. For example, you might want to do land use classification, weather monitoring, or rockfall detection. And finally, the channel model can be built on measurements from existing satellites. So using all of these three information, we can definitely design a better communication protocol that builds on top of the LoRa infrastructure. And that's the key insight that we exploit. And to do that, we build a data task-driven encoding. So how would you design a machine learning algorithm to compress an image and perform inference on them? Very simple approach. Just take the captured image, build a convolutional neural network to compress the image, then use the compressed image to do image reconstruction, and then perform an inference task. Easy? Why don't we just do this and deploy it on this satellite? Well, the reason is because it's not just a machine learning system, it's a machine learning plus wireless system. And there's this big villain of every wireless communication technology called a wireless channel. The wireless channel introduces two sources of information loss. One is discretization, which is basically, hey, you can't send a lot of large float numbers. You only can send 256 bytes of information. And second is noise and Doppler behavior, which corrupts the signal in a special way. To understand this, we created the training of this model in two stages. The first stage tries to make the model resilient to the noise and Doppler. For people, I know we are a computer science crowd, so I'll give you a brief primer on how does the noise and Doppler affect the bits that you're trying to transmit. So typically, the noise has a uniform effect across bits in corrupting the bits. So if you have, let's say 256 bytes, each bit has a uniform probability of being corrupted. Whereas intra-packet Doppler has a non-uniform behavior across bits because of the way we send the signal over the air. To show you, let's say we are sending some signal over the air, the intra-packet Doppler creates a small shift in frequency from the start of the packet to the end of the packet. And because of this, if like noise creates like a random bin being selected out of various bins in frequency domain, the intra-packet Doppler only shifts the frequency very close to the original data. This means instead of all bits being corrupted uniformly, only the least significant bits of the data are corrupted. This means there's a non-uniformity in terms of the bit errors. we actually modeled it effectively on all the past data that we have received from existing satellites. And we actually modeled the symbol error and the probability of error for each of the symbols. And it is definitely non-uniform. Now, if you train a model to just be robust to uniform distribution, it will not operate well on a real wireless channel where uh, Doppler is the one creating most of the bit errors. And hence, we actually created a bit flip black box that actually trains it on this non-uniform distribution of errors to ensure that the model is robust to this Doppler distribution of errors. Okay, now we have made our solution robust to the noise and Doppler. What about discretization? Well, as all of us know, discretization is a non-linear system, which means you can't just train a gradient over it when you are training a system. So we didn't complicate our life too much. We just froze the encoder layers and retrained the decoder to be aware of this discretization loss that we see because of the throughput limit. Apart from developing this channel-aware encoding, which takes together the information of the wireless channel and all the machine learning information that we want to achieve, we also developed solutions at the ground station to receive this data better so that we can do better Doppler estimation and detect these packets better. So the idea is slightly complicated, so I'll leave it off the talk, but I'm happy to chat with you about it offline if you have any questions. And then how did we evaluate the system? So for the receiver, we actually had our own base station that we deployed on campus at Carnegie Mellon. And then we actually used satellites that were launched by our collaborators in the sky. So these satellites were operating from Jan of 2021 to up till December of 2021. And while there were 3 satellites, only one of them sent a significant amount of data that we were able to use to understand the behavior of the wireless channel and try to run our system on. So on the right side, you can see the video of the satellite being launched and all the cool stuff. And then we also showed that all the measurements that we got from the satellites can be replicated by our channel model that we developed using those measurements. For example, uh, here is a example where the satellite packets were actually following the Doppler curve, and we can actually model the Doppler curve quite accurately. And then apart from this, we used existing Sentinel image patches because we did not have a camera on the satellite. And then our evaluation criteria was to reconstruct the images and to do land use classification. And the inference pipeline was simple. Hey, take an image, do this encoding using our clever encoder, do the discretization, send those bits over the air, noise and Doppler will corrupt the bits, we receive those bits and then do image reconstruction and land use classification. Land use classification is simple. Look at the land and tell what it is. Is it industry? Is it grass? Is it sea? Is it ocean? And just to show you what benefit our system achieved, by building better trajectory-aware preambles, instead of losing all the side packets, we were able to receive all the packets of the signal that were across a single pass over the sky. And in terms of image reconstruction, we were able to ensure that the features that were required for the image reconstruction and image classification tasks were preserved. For example, the outlines of a building, the behavior of the grass, and all of those things were preserved in the compression. And obviously, if you look at the image reconstruction results, we do significantly better than the baseline solution, a 4.56 PSNR improvement compared to the baseline. And we also achieve a 1.38 times improved accuracy in land use classification. Now, these were obvious now that the concepts were clear and why these would do much better. And if you see carefully, the kind of things that it gets confused between like highway and industrial environments is because of the fact that, hey, both are made of concrete. So in a blurry image, both would look like a gray blob. But using our system, which preserves the behavior of highway, which is like almost like a rope in grass, whereas industry is like a building, you can get much higher accuracy where the baseline usually gets confused. And with that, I would like to end the discussion of the second project. Before I conclude, let me talk a little bit more about all the work that I have done. Apart from just these 2 projects, I did a lot of work during my PhD studies and as a faculty. I built solutions for IoT analytics and inference. I've improved the IoT infrastructure capabilities, built sensing solutions where you can track these devices across a city scale deployment, and of course, CubeSat IoT connectivity. Apart from these things, I also built some of the fastest millimeter wave full duplex links and acoustic packet sensing solutions for Microsoft. And just before I finish, I want to acknowledge all the amazing funding agencies and amazing researchers and collaborators who helped me do all these projects. Now, before I conclude, let me tell you a little bit of what I'm exploring nowadays as a faculty. My future research is taking my wireless domain expertise to new application domains and technologies. And specifically, four areas that I'm extremely curious about are as follows. First is satellite IoT. And instead of thinking about just a single satellite, let's try to improve communication with satellite constellations that are becoming the norm for providing internet now. How do we develop better base stations for these satellite constellations? And can we improve the protocols to improve throughput and improve the services to the ground? The second is agriculture and forest IoT, where we are trying to build better sensors to actually give you an X-ray of a plant to detect diseases early on a farmland and help us understand better of how diseases progress on a farmland. Then, of course, I'll continue my work with Microsoft on building industrial IoT solutions. And then we are also exploring opportunities in underwater sensing to do biomass sensing underwater. And as we move towards a data-driven world, it is our responsibility as network engineers to build, augment new data sources, design wireless and wired communication technologies for these data-driven tasks, and then develop wireless-aware data-driven applications that understand the constraints of the wireless communication protocol. And if all of us work together, we can design a better data-driven world together. Of course, I'm always looking for students to join my new lab. So if you are interested in pursuing a PhD at UW, deadline is December 15 every year. Uh, and I would just end on this note and take any questions that you might have.
Thanks a lot, Akshay.
Mhm.
Any questions from anyone? If
Wow,
I
that's deafening silence.
Akshay, I have a very naive question.
Mhm.
This is Narayan from here.
Yeah,
Narayan
yeah,
here.
of course. Go ahead.
Hi.
Yeah.
So the question is that if we look at the number of IoT devices which are there today,
Mhm.
what is the kind of number that we are looking at, and how is it expected to grow over the, let us say, let's fix some small number, let's say over the next decade?
Mhm. Yeah, so that's a great question. And frankly, I started the motivation by saying home IoT devices, but home IoT is not going to scale that much as you might think. However, the real applications of these IoT devices will show up in industrial scenarios. For example, gas and oil platforms, or in agriculture applications where people are already using it to track their cattle like sheep and goats in large Australian farms, or detecting or deployments in large smart cities like Las Vegas is deploying them on all the trash cans. Sweden is already deployed them on some smart trash cans. So the scale is going to happen in outdoor IoT significantly more, and it will be built not by tech companies, it will be built by the application uh, users demanding the deployment of these devices. And most of these application users are going to either use low power, either LoRa or NB-IoT devices. And we are looking at a scale of roughly a billion devices by the end of this decade in industrial IoT scenarios. And we are already seeing it proliferating to improve accuracy and inference on an industrial scale. So if you go to any modern factory in China, you would see a lot of IoT devices being deployed for safety, for monitoring, to help with the automation of processes.
Thank you, Akshay. Yeah.
Yeah.
Anybody else has any questions? At a high level, Akshay, if I have to summarize your work, it covers four of the Panchamahabhutas. Sky, which is related to satellite, fire, and then soil, you showed that plant related thing, and then, of course, water. So only wind is remaining.
Well, technically, wind is covered because we also did a UAV project where we flew a drone in the wind. But yeah, I feel like much of my research is motivated by the users complaining about problems and me trying to solve them. And each of these problems had a unique origin of how I came to think of this problem. For example, 2020, all of you remember, it was the year of forest fires. Everywhere was we were hearing forest fires, and I was thinking, hey, if we deploy a large number of sensors, how do we actually get the data back from them? Similarly, for the satellite in a thing, all these satellite constellations are being deployed. So I was starting to think, hey, are we doing the best way to communicate with the satellites? And the answer was obviously no. We still are just scraping the surface. We are still using very old school protocols, and there's a lot more to explore there. And we did like the first scraping the surface of the exploration space, but there's a lot more to explore that we are hoping to do in the future.
Great. If there are no further questions, thanks a lot, Akshay, and
Sir,
thanks.
sir, I have one
Yeah,
question.
Amartya, go ahead.
Yeah, yes, yes. So, sir, you were talking about this large-scale deployment of these IoT sensors, and I assume that the data is being transmitted to some kind of remote server like that.
Mhm.
So, it's just a query, like, are you doing any sort of work, like, since there will be a latency to send those data back to a server and then performing the computation and again then doing some kind of inferencing task. So, offloading this kind of task to any kind of mobile devices or
Mhm.
any low cost computational thing.
Yeah, no, I think that's a perfect question. And in fact, this is a fight that we have been having for a long time. Hey, should we push the compute to the cloud or should we bring the compute back from the cloud to the edge to reduce the latency? And it really depends on the application. For example, in the case of the forest fire scenario, it definitely makes sense to do the computation at the edge instead of instead of the cloud. But it's other applications where, let's say, you're just trying to figure out how many devices upgraded to the firmware. Latency is not that important, so you can have a much more complicated model in the cloud, which you can potentially not deploy on the edge. So it really depends on the application, but this is a age-long fight, and it will keep being fought until edge reaches the capacity of what a cloud can do for most practical application, and we are quite far away from there. So if you want high accuracy but high latency, you go to the cloud, otherwise you deploy it on the edge.
Thank you. Thank you.
Any other final questions? Okay, so thanks Akshay for staying late for us.
Yeah, no worries.
Yeah, thanks a lot everyone for joining. On behalf of the department, let's thank Akshay for his time. And if in case you have any questions for Akshay, please feel free to write to him. If you want to apply to him, please get in touch with him as well.
Yeah, definitely. And thanks again, Rupesh and Narayan Swami, for inviting me. It always feels good to get